What is life? What is life chemically? Is it DNA? Not really, because DNA is a static storage of genetic information. Is it metabolism? Metabolism is a dynamic set of catalytic chemical processes, all interlocked, all moving together. Change one thing over here, it'll change something down there. This is life. Metabolism is the basis of life. So what is the chemical basis of metabolism? I don't think that point is elaborated on very much in chemistry at all, and I'd like to do it here. When we eat carbohydrates, carbohydrates are broken down into pyruvate. Pyruvate is converted into acetyl-CoA. Acetyl-CoA feeds into the Krebs cycle. The Krebs cycle generates NADH and FADH2, and they drive the electron transfer complex in the mitochondria, at the end of which is ATP synthase generates ATP. ATP is the fuel for metabolism. But that's not the only way we can get ATP. ATP can be generated from fats. Fats are broken down in an oxidative process to give acetyl-CoA, which similarly feeds into the Krebs cycle. So metabolism then is divided into two parts. The first part is catabolism, which is breaking down foods like fats and carbohydrates into simpler materials. Once these simpler materials like acetyl-CoA are generated, they can be reconstructed into things the cell needs, and that is anabolism. So metabolism then is first of all catabolism of food and anabolism of constituents of the cell, things that the cell needs to live. Let's think about glycolysis first. Glycolysis, that process by which glucose particularly is broken down to pyruvate. Glucose is a 6-carbon sugar. Pyruvate has 3 carbons. So how do we get from glucose to pyruvate in catabolism? Because remember, catabolism is breaking things down. If we look at the enzyme catalyzed steps, we should therefore be looking for the key one. And the key one is cleavage of a C-C bond. How does that happen? Well, let's ignore phosphorylations and all the different enzymes involved. That happens basically via a retroaldol reaction. Think of the aldol reaction, which could give glucose. That aldol reaction is fundamentally between glyceraldehyde and dihydroxyacetone. To get to the retroaldol reaction, we have to convert glucose to fructose. That puts the ketone 2 bonds away from the C3 to C4 linkage that's going to break. Okay, let's deprotonate the C4OH, feed in the electrons, generate a carbonyl, cleave the C3 to C4 bond, and then generate an ene with 2 alcohols on it, an enediol. That enediol, if it retautomerizes, may form dihydroxyacetone. The retroaldol reaction is the key step in glycolysis because it breaks the CC bond and converts C6, glucose, to C3, ultimately to pyruvate. Forget about all the phosphorylation steps and all the different enzymes involved, their different names. These are just peripheral to the chemical process that's going on. Of course, you need phosphorylation. Of course, you need those enzymes. But don't forget the basic chemistry behind this catabolic step. What about a parallel to glycolysis, which is anabolism. Well, if we have too much pyruvate, we might want to put it away as glucose and then glycogen. So how do we do that? Well, the pyruvate is converted back to glucose via gluconeogenesis. And what is gluconeogenesis? Fundamentally, in terms of chemistry, it's an aldol condensation between the enol of dihydroxyacetone phosphate and glyceraldehyde. It's exactly the reverse of glycolysis. Of course, the enzymes are different. Of course, the phosphorylation states may be different. The energetics is different, but that's fundamentally what it is. A catabolic step for glycolysis and an anabolic step for gluconeogenesis. So what is fatty acid oxidation in catabolism? Well, fatty acid oxidation is trimming off of 2 carbon fragments. And how does that happen? Well, I already have a video on the Claisen condensation. That's an ester-ester condensation, basically, and that's published. A retro-Claisen condensation, especially of acetyl-CoA, what would that look like? Well, begin with the product. The product is CoA carbonyl, CH2, carbonyl methyl. That's our 1,3-dicarbonyl from an ester-ester condensation. Attacked with acetyl S- on the carbonyl, generates a tetrahedral intermediate that collapses and breaks the CC bond, giving an enolate of acetyl-CoA. So imagine now a fatty acid converted to an acetyl-CoA ester. That fatty acid can be oxidized at the beta position in 3 steps. The first one is dehydrogenation, gives an alpha-beta unsaturated compound. The second one is a hydration in the conjugate addition sense. That gives a 3-hydroxy ester. And the fourth one is oxidation of that, probably with NAD+. That 1,3-dicarbonyl undergoes a retroclaison, gives us a molecule of acetyl-CoA to feed into the Krebs cycle, and a fatty acid ester of CoA is regenerated. That can be dehydrogenated, hydrated, and oxidized again for the next retroclaisen condensation to give another molecule of acetyl-CoA and regenerate an acetyl-CoA of the fatty acid ester reduced by 2 carbons again. The process is repeated. Dehydrogenation, hydration, oxidation, NAD+, retroclaison, acetyl-CoA, Krebs cycle, 2 carbons less. So in that way, 2 carbons are trimmed from the fatty acid chain in each step, and beautifully we generate acetyl-CoAs put into the Krebs cycle. Catabolism, very efficient. Oxidation of fatty acids is a very efficient way to generate, ultimately, energy via ATP. What about going backwards? Let's say we have too much acetyl-CoA and we want to store it as fats in some cells. How do we do that? Well, we have to generate CC bonds. So the first step is to take acetyl-CoA, form an enol or an enolate, whichever way you want to think about it. Of course, this goes on in enzymes, and react with CO2. CO2 generates malonyl-CoA. Malonyl-CoA is a very special way of generating enolates of acetyl-CoA when they're needed by decarboxylation. Decarboxylation of malonyl-CoA generates an enolate in situ, which adds to acetyl-CoA. That generates a Claisen condensation product, an ester-ester condensation. 2 carbons plus 2 carbons, 4 carbons. The beta-carbonyl can be reduced by NADH to the corresponding alcohol That alcohol is dehydrated to give an alpha-beta unsaturated ester of CoA, and that alpha-beta unsaturation is hydrogenated by FADH2 to give the corresponding 4-carbon fatty acid ester of astar-CoA. That can undergo another Claisen condensation, generate another 1,3-dicarbonyl, which is reduced again by NADH, oxidized, dehydrated to give an alpha-beta unsaturated system, and reduced FADH2 to give 6 carbons in a row. And you can see how we can keep going. 8 carbons, 10 carbons, 12 carbons. A fatty acid of any even number of carbons is built up by this beautiful series of catabolic reactions involving C-C bond formation via Claisen-type enolate reactions, or enol reactions, however you want to think about it. Let's look a little bit deeper into the Krebs cycle. I already have a video on the Krebs cycle, but let's zoom in on some of the early steps. Let's take astar-CoA, form an enolate or an enol, and add that to oxaloacetic acid. That gives citrate in the Krebs cycle. Now, of course, catabolism and metabolism is not restricted to humans. In other organisms, these steps take a different form. But almost inevitably, when we look at catabolism, we're looking at cleavage of C-C bonds. When we're looking at anabolism, we're looking at formation of C-C bonds. So for instance, if we look at the glyoxylate cycle in bacteria, fungi, and some plants, isocitrate is a C6 unit, succinate is a C4. The retroaldol generates an enolate of succinic acid. You may find it easier to picture the forward direction aldol reaction. So the aldol reaction of the enolate of succinic acid with glyoxylate gives isocitrate. So what is life? Life is metabolism. What is metabolism? Fundamentally, metabolism is breaking down carbon-based molecules into smaller ones via retroclaisen or retroaldol reactions, because these cleave C-C bonds. What is anabolism? Anabolism can be construction of many things, but anabolistic steps to generate carbohydrates again, or generate fats again, and generate other things can involve aldol or Claisen reactions. Enolate and enol reactions with aldehydes are fundamental to life. Thank you very much for listening. I hope that helps you with the studies. Bye-bye.